The main program class is the entry point of a robot assembly system. It provides menu-based interface for user to build customized robot with various features. Store and manage created robot instances. Operate individual robot through specific action like powering up, moving, scanning, and combat. A scanner object to handle user input. A list robot to store all created robots. A robot assembly line object which acts like factory to build robot instances. The menu is handled inside a while tree loop. Inside the following three options: build new robot, operate existing robot, and exit. The menu continues to show until the user select option 0, which is exit. The user select build new robot. The build robot method is executed. It performs collect basic robot details like robot name, model, number, and eye color. Then it asks the user to choose an input sensor type like thermal, radar, optical, power source like solar, battery, hydrogen, arm strength, leg mobility, weapon type like laser, missile, weapon power level. When the user chooses operate existing robot, it displays a list of all robots with the name and model number, prompts the user to select a robot by number, operates a submenu for selected robot with the following actions: power up, move, scan area, combat, and view status shown robot's name, model, and power status, and return to name. The center text method used to centers a string within 50 characters for better visual alignment in the console. If the text is too long, it returns as it. The display box method display a message inside the box with border using center text in box. To center the content, used to highlight important info. The center text box method used to center text within a 48-character box. It adds equal spaces on both sides to keep the message neatly aligned in a bordered box. The display menu method prints a title menu with a border and neatly formed option. It provides user interface clarity and structure. The get choice input method display option as a menu and asks the user to pick one. It ensures the input is valid and returns the selected option as string. The get string input method prompts the user and read the line of text it used to get simple string input like name or model numbers. The get input method prompt for integer and handle invalid input using try-catch block. Ensures the numeric input is correctly entered. The get input method gets an integer from a user with a specific. The get int input method get an integer from user within a specific range. Keep asking until the input within allowed limit.
Greetings, Sir Patrick. My name is Prince Paulo Panganiban and allow me to discuss our robot class. This robot class inside the Robot Factory package is a blueprint for creating and managing robot objects in an object-oriented manner. This class is structured to model a robot composed of various components: head, torso, arms, legs, and a weapon. It encapsulates the robot's identity and behavior and provides methods for assembly, activation, movement, scanning, and combat operations. The class begins by declaring several private fields, name and model number, to store the robot's identity, and object references to each robot part, which will be set later during assembly. A Boolean powered off flag keeps track of whether the robot has been fully activated. The constructor public robot string name, string model name initializes the robot's name and model number with the given parameter and sets powered up to false by default indicating the robot is inactivate after creation. The assembly method accepts instances of each robot part and assigns them to the robot's internal references, simulating a physical build process. The power up method is responsible for activating each robot component. It first calls the activate method on all parts, assuming these are defined in the respective classes. Afterward, it checks whether all the parts have been reported, being powered using is powered up methods, and sets the power up flag accordingly. A successful or failure message is printed depending on the result. The move method allows the robot to move, but only if it has been powered up. If not, an error message is displayed. When powered, the method retrieves the movement speed using leg.moveSpeed and prints a message with that speed. Similarly, scan area performs an area scan using the robot's head, but only if powered. It prints success feedback based on the result of the head scanner area. The combat method checks the power status first. If the robot is activate or inactive, it calculates the total attack power using the punch power from the arms and attack power from the weapon, then outputs the combined attack details. Finally, three gathered methods, get name, get model number, and is powered up, are included to allow external classes to access these private fields in a controlled manner. Overall, this class demonstrates solid encapsulation and separation of concerns, simulating a modular robot that functions only when fully built and activated.
Head class in the Robot Factory package. This class shows how the head component manages sensor operations and power status. This class contains three variables. The first one is a boolean powered up that is initially false, and two string variables for eye color and sensor type. The constructor takes eye color and sensor type as parameters and initializes these values while setting powered up to false by default. The class provides three methods. First, activate, which turns on the head and displays a message. Second is scan area, which simulates scanning with the sensors and returns true. The third one is powered up, which simply returns the current power status. When activated, the head prints a message showing which type of sensors are being used. Similarly, when scanning, it announces the sensor type being utilized for the scan operation.
So, hi everyone! Today we're going to explore the torso class in our robot factory system and how it connects with all the other components using object-oriented programming principles. So let's look at the torso class first. In our robot design, the torso serves as the central power distribution unit. Here's what makes it special. So the torso class has two main properties. First, we have powered up, a boolean that tracks activation status. Second, we had power source, that's storing what type of power it uses. So the constructor takes a power source parameter and initialize powered up false, meaning the torso starts in an inactive state. So the active method powers up the torso and prints the confirmation message with the power source type. Its power up is a simple getter method that returns the activation status. So now let's see how the torso connects to everything else. To the robot class integration, the robot class has a torso as one of its components. During assembly, the torso gets created with a specific power source. When power up is called on the robot, it activates the torso first. So, Power-up distribution. The torso powered-up status is a crucial because the robot checks this along with other components to determine full activation. And also, it shows the torso role as a central component. If it fails, the full robot fails to power up. And also, we have assembly line. In robot assembly line, the torso gets created based on user power source selection. It then passes to the robot during assembly. So, let's see this in action. When we run the program and build the robot, the user selects a power source like nuclear power. Second, this creates a torso instance with a power source. And during operation, activating the robot shows the torso activation message first. And the robot checks torso is powered up to determine overall status. So this design demonstrates the key principles. First, we have encapsulation. Torso internal state power up is private and accessed through methods. Second, we have a composition. Because it's composition, the robot is composed of a torso and other parts. And single responsibility. Torso only handles power related functions. So, to summarize the torso class, the manage the robot's power system. And also it coordinates with other components through well-defined interface. So, try modifying the torso class yourself. Maybe add a power level property or different activation modes. Thank you for watching.
Hello and Dangal greetings. I will be the one who in charge to discuss to you the ARM class. So the ARM class in Java is just a simple representation of a robotic or mechanical arm system that can be activated and has a measurable strength. It has two private instance variables, which is powered up, a boolean that indicates whether the arm is currently turned on, and the strength level, which is an integer representing how strong the arm is. By default, when the new arm object is created using the constructor, the arm is set to be not powered up, so the power up equals to false, and its strength is initialized based on the value passed to the constructor. So the class provides several methods to interact with the arm. The activate method is used to turn the arm on. When called, it sets the power up variable to true and prints a message to the console indicating that the arms have been activated along with their current strength level. This could be useful in simulation or game to visually confirm that the arm is now active. Another important method is the punch power, which simplify returns the strength level of the arm. This can be used in scenarios where you need to calculate the force of a punch of or any action the arm performs. For instance, if the arm is being used in a battle simulation, this value could determine how much damage is dealt to an opponent. Lastly, the power the is powered up method is a getter that returns the current state of the powered up flag. It allows another parts of a program to check whether the arm is activated before trying to use it for an action. This adds a layer of safety or logic control, preventing the arm from being used unless it is properly powered. So overall, this class provides a basic structure for modeling a controllable and strength-based robotic arm, with the methods that reflect common operations like powering on and checking status. It could be serve as a foundational component in large robotics, gaming, or simulation application.
Greetings everyone, I am Sabrina and I will present the class which is named Legs. So this Java class represents um, a component of a robot where um, implied by the package named Robot Factory. Now, first, the package which is package com.robot factory. This line places the legs class in the com.robot factory package. It helps organize the code and avoid class name conflicts. Next will be the class declaration, which is public class legs. Um, wait. Hmm, variables. Variables, which is the private boolean, powered up, and private in mobility level. The powered up variable indicate whether the legs are turned on. Um, we indicate whether the legs are turned on. Like if we say boolean, it is um, which will be run by true or false. Next will be the mobility level. This is an integer value representing um, how fast or agile the mobile legs are. Next set of codes will be the public legs, which is the constructor of this code. This constructor initializes a new leg object with specified mobility level. The legs are not powered up when first created. Next will be the method. Um, these methods turns on the legs by setting powered up to true. I already explained it earlier, like the powered up variable is in Boolean. It also prints a message showing the current mobility level, which is legs activated with mobility. Another method will be the speed, the move speed. Um, the move speed returns the mobility level, which likely corresponds to how fast the legs can move. Next method will be the powered up. This returns whether the legs are currently powered on or not. To generalize the code, the leg class encapsulates the idea of robotic leg within a certain mobility level. The leg class also allows the legs to be activated through Boolean variable. The legs class provides method to check their speed. As I showed earlier, there's a method for speed and um, there's also a method to check if the robot legs are powered up or not. That will be all for the legs class. Thank you.
The weapon class is responsible for managing the robot's attacking capabilities. It has three main attributes. First is the weapon type attribute. It is a string that defines what kind of weapon the robot has, such as a laser or a missile. Second is the power level attribute, and it determines how strong the weapon is. And third attribute is powered up. It is a boolean that tracks whether the weapon is active and ready to fire. Weapon class also has three key methods or functions to control the weapon. First is the activate method. It turns on the weapon, setting the method to true, and prints a confirmation message. Second is the powered up method. It checks if the weapon is active. And the third is the attack power that returns the weapon's power level, if active, or zero if not. Essentially, this class ensures that the robot can power up its weapon, check its status, and execute attacks effectively.
So, in our robot factory system, the robot assembly line class acts as the central factor that builds complete robots, and it connects all parts from the head to the weapon to create a fully functional robot. Let's break it down. So first, we had a build robot method. So the robot assembly line class used the builder pattern, an OOP pattern that simplifies complex objects creations So instead of manually creating each part in main program, the assembly process is centralized here. So this class has only one job, assembling robots. So it doesn't handle operations or user input, just constructions, clean and modular. So how it works? So first we had a head, head equals new head, open and close parentheses, eye color, sensor type. So the robot assembly had a component using the user inputs. So first we had head. So inside the head we had eye color, sensor type, and also we have a torso. Inside a torso we have power source, and arms. Inside in arms we have strength level, and legs we have mobility level, weapon we have type and power level. So all parts are combined into the robot class using the assemble method, which is robot.assemble, open and close parentheses, head, torso, arms, legs, and weapon. And also, the fully assembled robot is returned to the main program for use. For example, powering up, moving combat. So the connection to the other class of this robot assembly is it relies on every component class, which is head, torso, arms, and etc. to build a complete robot. And also the main program calls RobotAssemblyLine that builds robot open and close parentheses with user inputs, then stores the assembled robot in a list. And also the robot class doesn't create its own part. It's just receive them from the robot assembly line via assembled open and close parentheses. And also to display the solid principles, we have a encapsulation. So each part, head and arms and etc. manage its own state. Like for example power up. And also we have a composition over inheritance. So the robot has parts composition instead of inheriting from them. And also we have a main program that handles user interactions, robot assembly line, builds and robot operates no overlap. And also in conclusion, to summarize all of this, the constructor robots part by part, so it keeps objects creation clean and centralized.